let's talk about electric flux and Gauss's law. So we can define a flux of electric field in the same way we defined it for fluid flow, which is a different vector field. We often call or write the flux as capital Phi, and it's going to be the integral of E dot dA. Okay, so the same ideas in terms of how you calculate this carry over from the fluid flux. You have this dot product, so it matters the direction of the field through the surface. Now, interpreting this physically, the best way I can give you to think about it is it's basically counting the number of field lines that go through the surface. Okay. Now, the number of field lines is arbitrary. When you draw the picture of an electric field, you get to pick how many field lines you draw. Let's take a point charge here, and I'll draw that many field lines. But of course, I can draw a lot more if I wanted to. So the number of field lines is not the answer to this integral, okay? It's not going to give you a unit number of field lines. But if you're going to compare things in a relative sense, you can do it by using field lines. If I want to ask the question, what's the flux through, say I'll take this surface here, compared to a surface that's a similar size that I put out here, okay? If I look at these two surfaces, I can tell right away which one has more flux through it because I've drawn accurate field lines, and I see that 3 field lines go through the inner surface, surface 1, and only 2 go through the outer surface. So I can immediately write down that phi 1 is bigger than phi 2. And we can understand that from this expression here because the electric field at the location of surface 1 is greater than the electric field at surface 2. Therefore, if I argue they're roughly the same area, even if they're not in this case, I mean that justifies quantitatively why the flux is less in those between in case 2 versus case 1. Okay. And all right, and the angle of the field matters. The angle of the surface matters too. Okay, so it's you still when you have an angled surface can think about it as counting the number of field lines it goes through. But if I angle the surface, I get less field lines. And one good example of that is if I take a uniform field, and let's just take 3 of those field lines. Let's imagine my surface is exactly this long. Okay, so it just picks up these field lines at the top of the bottom. If I rotate the surface now, I'm necessarily going to miss. Oops, that's not a very good drawing. Let me try again. I'm necessarily going to miss the top and bottom field line because I have the same length, and now I'm pointing it or rotating it over. It's going to roll over with some arc here, and as I roll it, I'm going to miss this top and bottom field line. Okay. Now, of course, it's not going to be a discrete jump in the flux. This is just an argument as to why the flux should go down. As I rotate it, I'll pick up less field lines. Okay, and so again, I can draw as many field lines as I like. But if you imagine changing the angle of the surface, I'm going to pick up less of them than I would if I oriented the surface so that it's the normal is parallel to the electric field. Okay, which is this first surface here. Okay, good. All right, so the number of field lines gives you a sense as to the flux through a surface. Again, the flux can also have a sign, so make that point. Again, the normal vector that you choose for your surface is completely arbitrary at this point. You get to choose the surface and the direction of the normal. Okay, but if it turns out that for some reason, you were to choose, let's take, let me get a different color here. Let's take this surface, and if I chose this to be my normal vector, in this case, the flux would be less than 0. Because now n dot v would give me a negative number. Okay. All right, and so it can be negative. It counts the number of field lines. What I want to talk about now is flux through a certain class of surfaces, which is going to be closed surfaces. So let's imagine a closed surface. It can be any shape you like. Okay, and so imagine this is a closed surface. When I say closed surface, I mean a surface that encloses a volume, that separates an interior volume from an exterior volume. So, this blob is hard to figure out what it's going to look like out of the page, but if I take a sphere, for example, or a cube, Okay, this is what I mean by a closed surface, a surface that has walls on every side. Okay, and you separate one volume from another. Okay, and we can talk about now the total flux through this closed surface, and we'll usually write it as a closed integral, okay, of E dot dA. So the integral over a closed surface, like that. All right. Now this quantity has some significance. Okay. If you allow me, I'll go back to the fluid analogy for a second. Here, let me switch pages. And the fluid analogy, if I talk about a net flux into a volume, it really tells me the rate of accumulation of water within that volume. Okay, so if I have water that flows into one side of the box and doesn't flow out of the other side, then it must have stayed inside the box. Okay, so if I have, let's take my box here, and well, let's take a good or hopefully easy to understand example, which is a box that's open on the top. Okay, again, the surface that I'm defining doesn't really have to be a solid surface. It's an arbitrary, imaginary surface. But let me have inside, let's do it this way. I'll have my surface, then inside the surface is a bucket. Okay, and what I'm doing is I have a spigot up here. Okay, and I'm flowing water into the bucket. So as I do this, water flows into my cube volume, but not out. Okay, so this is going to be a case where the net flux of matter into the box is going to be non-zero. Okay, so I've got stuff that flows in, but it doesn't flow back out again. And another example of having a non-zero net flux would be if I had the spigot inside the box. Okay, so again, I can arbitrarily define where my box is. I can just put it around the spigot. Here it is, my source of water. So now I have water that flows out of the box, but not into the box. So in this case, I also have a net flux that's not equal to zero. It'll have the opposite sign of this case. Now, to get the sign, I have to take a convention for the normal vector. And so the convention we're going to use as we talk about electric flux is that the normal vector always points outward. Okay, so if I have a sphere, the normal vector is always outward everywhere. And so if I have a box, it's outward in all directions. Okay, and so in that case, this example would actually be a negative flux, and this example a negative net flux, okay, and a negative positive flux, okay, would be in this case. Now that doesn't seem to make sense from a point of view of fluid, because in this case I'm actually accumulating water in the box, and you would think that would be a positive value, and this would be negative because I'm losing it. So you might choose the other convention for water flow, but for electric field, it turns out having an outward normal is useful because it tells you when you have positive charge inside the box. Okay, and we'll get to that now. So, all right, so for fluids, I need basically a net sink of water, a way that water gets trapped inside the box to have accumulation of flux, or a net source of water inside the box. Now for electric fields, again, I'm counting field lines that go through the box. So if I take a closed volume like a sphere, and let me put a point charge over here, you know, any field line that comes off this point charge, I mean, this is not really drawing the electric field correctly, but it should go out straight here. But any field line that enters the volume will leave the volume. Okay, that's true for all field lines in the case that I'm drawing right here. So in this case, I get no net flux, electric flux through the volume. Now if I change the location of my volume and I put the point charge inside my volume, now I have a situation where field lines start inside the box. That's just like this case up here, where I have the spigot inside the box. Now my spigot, my source of flow, source of electric field, is inside the box, and so I get a net flux that comes out of the box. Okay, so the only way for net flux to go into a closed volume or out of a closed volume is if there is a charge inside. Okay, really if there's a net charge inside. Okay, so if I imagine now a negative charge being inside my volume, then field lines will, on average, I mean on net, I should say, not on average, will enter the box or enter my volume. Okay, and there will be, in these two cases, the integral of E dot dA over the whole surface is not equal to 0. Okay, all right. So it turns out that um, it can be shown that the net flux, okay, for a closed volume, which we've written as integral over the closed area, the surface bounding the volume, dot dA, is equal to the net charge enclosed, we call it Q enclosed, divided by epsilon naught. Okay, and this is Gauss's law. All right, and so if I have no net charge inside, but charge, so imagine I have some charge inside my volume, but I have equal amounts of positive and negative charge inside. So if I draw field lines for this case, it turns out that any field line that leaves one charge has to come back to the other one. Okay, like this. The only way to have field lines escape to infinity is to have a net charge in the region. That's how field lines can escape. If I have the same amount of positive and negative charge, the field lines will connect between the two. And so whatever field line exits the box, exits my volume, will come back in. And so the net flux to the surface will remain 0. And the only way to have a net flux, again, is to have the more positive charge than negative charge, or vice versa. Okay. All right, let me stop there.